This is AP Calculus 6-2, Part 4, the Trapezoid Rule. We have learned already how to do the left Raman sum, the right Raman sum, and the midpoint rule. And to just review those, if we were doing the left Raman sum, we would draw rectangles from the left to the right. Some of them would be an overestimate, some of them would be an underestimate. And that, if we take the area of those rectangles, add them together, we get the area of the curve. For right Raman sums, we draw the rectangles from the right to the left, and again, some would be over, some would be under. We would add them all together to get an estimated area. For the midpoint rule, we would draw the rectangles from the center of each interval. Part of each rectangle would be above, and part of each rectangle would be below our actual curve to give us the midpoint rule. The rule that we haven't talked about yet that I think is usually the most accurate is the trapezoid rule. Let's separate this area under the curve from 0 to b into 4 equal subintervals. And if I do that, for the trapezoid rule, the first thing I'm going to do is I'm going to draw a line up from where each of my subintervals would begin on the bottom. And this time, instead of drawing rectangles, we're going to draw trapezoids. And to do that, we're going to take each point where these line segments end up on our graph. We're going to draw the point, then we're going to draw straight line segments from each point to the next point. So from here to here, I'm going to draw a straight line segment. And you see that line segment is very close to that curve itself. For this one, I'm going to draw a line segment right there. For this one, I'm going to draw a line segment here. And for this one, I'm going to draw a line segment here. And you can see those line segments are very close to where the actual curve is. So this is going to be a very close estimate. And the idea is, just like before, the more rectangles we divide this thing into, the closer and closer our area is going to get to the actual curve. So what if I took this same function and instead of having 4 equal intervals, I made 8 equal intervals? So I put another line segment halfway between each of the existing line segments to form 8 segments. If I do that, draw my dots where those line segments intersect my f of x curve, and then draw my line segments to connect the trapezoids, you can see that as I do this, the closer my intervals are to each other, the more accurate this trapezoid rule becomes, because these little straight lines look like there is no gap. Now we know there is a little bit of gap in some spaces, but because of the thickness of my marker, and that's fairly thin, we're not going to be able to actually physically see those gaps. So we know it's not the exact area under the curve, but it's going to be extremely close. And the next thing you need to understand with this is the area of a trapezoid. The formula for the area of the trapezoid is area equals 1/2 the height times base 1 plus base 2. With these trapezoids, they will all be in that direction, where your height is going to be that direction. It's the height defined in a trapezoid is the distance between the 2 parallel sides of the trapezoid. That is what the height is defined as in geometry. So my height is going to be this distance between each of my trapezoids. So if you think about that, each of these trapezoids is going to have the exact same height. They also would all have a 1/2 in front, because that's part of the trapezoid rule. Now, for the base 1 and base 2, if you think about that, for this first trapezoid, this would be your base 1, this would be your base 2. For the second trapezoid, this would be your base 1, this would be your base 2, and we could continue that pattern. This is base 1, base 2, 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 base 1, base 2. So now, if you think about this, every one of the middle lines here is going to be a part of 2 area formulas, if I were to write it out, because this trapezoid has this side as its base 2, but this trapezoid has that same side as its base 1. So every side in the center part is considered a base 1 and a base 2 at some point. Every side that's outside, the end sides, only show up once, because this is going to be in base 1 for the first rectangle, but it's never going to be a base 2. This is going to be a base 2 in the last rectangle, but it's never going to be a base 1. So every one of these lengths is going to be used twice. Each of these lengths will only be used once. In front of the formula, we have a 1/2 height. The height for each of them is going to be the same. So if we were to do this trapezoid rule and write this formula out every single time, it's going to get pretty time consuming, because that's going to be a lot of extra writing that we're going to have to do. But I'm going to show you in an example how this can be condensed into something very simple. If you can remember that the middle bases are all used twice and the outer bases are each only used once, the width between is the same and they always have that 1/2. I'm going to do the y equals square root of x example that we did earlier for the left Raman sum, right Raman sum, and the midpoint rules. I want this to be separated into 4 equal subintervals. And then when I draw my top lines for my trapezoids, this line is going to go here, this line right here, this line, and then this line, connect those 2 dots, is about right here. And you can see this one's not a trapezoid at all. It's actually a triangle. But if you think about that, this base 1 that normally would have been there is just going to be a 0 because it has no length. So if we think about the trapezoid rule, if this goes from 0 to 1, this would be at 1/4, this would be at 1/2, this would be at 3/4. If we plug each of these x values into the equation, we would end up with ordered pairs actually on our function. So if I plug 0 in, this ordered pair is going to be 0, 0. If I plug 1/4 in, this ordered pair would be 1/4, 1/2. If I plug 1/2 in, this ordered pair would be 1/2, 1 over square root of 2. If I plug in 3/4, this would be the ordered pair 3/4 square root of 3 over 2. If I plug in 1, this would be the ordered pair 1, 1. So if we're thinking about the heights of each of these, the height here of base 1 is going to be 0. The height of this line segment is going to be 1/2. The height of this one is going to be 1 over square root of 2. The height of this one is going to be square root of 3 over 2, and the height of this one is going to be 1. So if we know those heights, that will help us with our formula. So I'm just going to write those in. This was 0, this height was 1/2, this height was 1 over square root of 2, this height was square root of 3 over 2, and this height was 1. Now I'm going to do my trapezoid rule. Remember, the area of a trapezoid is 1/2 the height times base 1 plus base 2. And I want you to make some connections here that happen for every single trapezoid rule that you will do. All right, so I'm just going to write the formula, this part of the formula, for each of these trapezoids. So for the first one, my 1/2 is in there. The height of each of these intervals is going to be 1/4 because the distance between each of these numbers that we plugged in is 1/4. For the first trapezoid, my base 1 was 0 because there's no length there. My base 2 is 1/2. That's the formula for the first trapezoid. I'm going to add to that the formula for the second trapezoid. The 1/2 is part of the formula. The height is the same for all of these. My base 1 in this one is 1/2. My base 2 in this one is 1 over square root of 2. In my third trapezoid, the 1/2 times 1/4 is consistent, 1/2 times the height. My base 1 is 1 over square root of 2. My base 2 is square root of 3 over 2. For my last trapezoid, I have 1/2 times my height 1/4, staying consistent. My base 1 is square root of 3 over 2, plus the base 2 is 1. So we've got this long, drawn-out expression that we're going to have to find the answer of. Well, let's just think about what each of these terms have in common. Now understand, anything multiplied together, all of these things are multiplied together, that's considered one term. This is considered one term. You learned this in algebra. This is considered one term. This is considered one term. Okay? Well, what do all of those terms have in common? Well, they each have a 1/2 and a 1/4, right? 1/2 and 1/4. In other words, they each have a 1/8 in common. So can't we take out a 1/8 and multiply every term by 1/8? We've distributed it out. We've factored it out. That's an algebraic rule. You can do that. So each of them has a 1/8. I'm going to take the 1/8 out. I'm simplifying my formula. This will happen every single time, and I want you to see this. Then notice in what's left of each term. This one has a 0. This one has a 1/2. This one has a 1/2. This one has 1 over square root of 2. This one has 1 over square root of 2. This one has square root of 3 over 2. This one has square root of 3 over 2. This one stands alone. So the outside lengths only show up once. So that 0 and that 1, I'm going to put those by themselves. But notice the rest of them. This shows up twice. So I'm going to have 2 times 1/2. This shows up twice. So I'm going to have 2 times 1 over square root of 2. This shows up twice. So I'm going to have 2 times square root of 3 over 2. And that finishes out my expression. So now I have a very simple expression to find the area under this curve. My height, if you think about that in terms of where this endpoint is and where this endpoint is. Well, 1 minus 0, the distance between the two endpoints, is 1. I'm dividing it into 4 equal sections. N is 4. So this number right here is the formula B minus A, right? This endpoint minus this endpoint is the 1, divided by N. N is how many equal sections you're dividing it into. So B minus A over N for this formula would be 1 minus 0 over 4, or 1/4. Look at that. It's this number, okay? If we take this number, multiply it by the 1/2 in our formula, that's the other number out here, giving us what we would multiply the terms by. So that's how we can compute this without going through all of this. So when I put this in my calculator, I end up with the decimal 0.643 as my estimated area underneath the curve. So here is an example of the trapezoid rule. You can see here in blue we've got the f of x function. We have separated that f of x function into 5 subintervals. Notice those subintervals are not of equal length. That's okay. Sometimes, depending on the problem and the situation you have at hand, the widths are not going to be the same, but you can still use these estimates, the left, right, and midpoint Riemann sums, to find the sum of the area under the curve. So don't worry that they're not equal distance. This is just the first time we've seen that. It doesn't mean anything. That's fine. But the big difference here is that you need to notice we're still going to draw lines up to our f of x function from where our interval point is. But now instead of drawing rectangles, we're going to be drawing trapezoids. So we're going to connect those two intervals by a diagonal line. Now this one looks very close to a rectangle, but that probably is not parallel to this. Could possibly be, depending on the function. This trapezoid connects those two. Here's another one and another one. And you can see that by doing trapezoids, the area that we're leaving out, or the area that we have that is extra, is very, very, very small. So it eliminates a lot of the error that you have when you use rectangles. We saw that the left Riemann sum, the right Riemann sum, one would be an overestimate, one would be an underestimate. We saw that the midpoint rule would be somewhere in between those two. The trapezoid rule is probably, in my opinion, most of the time going to be your closest estimate, because you're using a shape that is closer to the shape of your curve to get your estimate. So again, trapezoid rule is going to be a really, really close estimate. Not perfect, but probably closer than any of your rectangular method. And so here you can see another one. Now we're going to estimate the area under this curve again, but this time we're going to use the trapezoid rule. It's telling us to use 5 equal subintervals. So I'm going to make that picture a little bigger and draw my subintervals. So if I draw my dots on the curve, where these intervals touch the f of x curve. These would be the dots that I'm using. And then I'm going to draw a trapezoid. So from here to here, I'm going to draw a straight line. I'm going to draw another one here, here, my fourth one. And you can see that's very close to the curve. And here. And they usually don't ask if this is an overestimate or an underestimate because it is so close. Okay, so if we're thinking about the trapezoid rule, we know that the area of a trapezoid is 1/2 the height times base 1 plus base 2. And when we were doing this on the whiteboard, we said that that 1/2 is going to be common for all 5 of the trapezoids. The height is going to be the same for all of the trapezoids. So you can see here that the heights are all going to be 1, and we've talked about that before when we were dealing with the rectangle. These are all 1. So they're all going to have a 1/2. They're all going to have a height that's 1. And then the bases are going to be the same for the terms in the middle. In other words, if I set up this trapezoid, I'm going to have its area as 1/2 times the height times its base 1 is 2 and its base, the second base 2 is 3. So that would be the area of my first trapezoid. We're going to add that to the area of the second trapezoid. Well, again, we have 1/2 times 1 times 3 plus 4. For the third trapezoid, I'm going to go down here. We've got 1/2 times 1 times 4 plus 3. For the fourth trapezoid, we've got 1/2 times 1 times 3 plus 2. So you got this side is 3. For the last trapezoid, we've got a 1/2 times 1 times 2 plus 1. If you notice here, every single one of these has the 1/2 times 1. So using that trapezoid rule, that 1/2 times 1 can come out of that function. Then if you think about the inside of what we're dealing with here, well, the outside term of 2 only shows up one time. But look at the other numbers. The 3 shows up twice. The 4 shows up twice. This 3 shows up twice. This 2 shows up twice. So all of the middle vertical lines show up twice. So I've got 2 times 3 plus 2 times 4 plus 2 times 3 plus 2 times 2. Plus that last number, the 1, only shows up once. So this would be my trapezoid rule. And so I can do this pretty simply. I'm going to have a 2 plus 6 plus 8 plus 6 plus 4 plus 1, which gives me 1/2 of 27. And half of 27 is 13.5. And if I remember correctly, I think that was the same answer that we got for the midpoint rule. So in this case, the midpoint rule and the trapezoid rule are very, very close. That does not always happen, just occasionally. And then the last example is the same example we started with earlier. This time, though, we are going to find D, estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding the trapezoid sum with 3 equal subintervals. So we're going to separate this again into 3 equal subintervals and figure out its sum using the trapezoid rule. So I've made my picture a little bit bigger. I'm going to draw in my trapezoids, and remember this one is for 3 equal subintervals. So if I do that, I'm using these points for my 3 equal subintervals. My widths again of each trapezoid, or my heights in this case of each trapezoid, is going to be 4. And then to draw those trapezoids, there's my first one, second one, and third. And you can see it's very close to where the actual blue line was. So if we think back to the last example, we know that every one of these trapezoids has a 1/2. If we think about the area, I'll just write that down again. Area equals 1/2 height times base 1 plus base 2. And we said in the last example that the 1/2 height is common to all of these trapezoids. So I'm going to put the 1/2 times 4 on the outside, because that is going to multiply by everything on the inside. And then we said that the first term shows up once, the last term shows up once, and all the ones in the middle would show up twice. Now remember, this is going to be my base 1, this is going to be my base 2 for the first trapezoid. This will be my base 1 for the second trapezoid. This will be my base 2 for the second. So this will be my base 1 for the third trapezoid, and this will be my base 2 for the third trapezoid. So if you look at this, this only shows up once, that length. This length is showing up twice. this length shows up twice, this length shows up once. So the first and last only show up once. So the first length at 0, we're at 40. So the 40 only shows up once, plus this height, or this base at 4 is 36. It shows up twice, so that's 2 times 36. This base at 8 is 26, so that shows up twice, 2 times 26. The last base only shows up once. The base at 12 is 8, looking at my table. And if you have a table like this, sometimes you might not necessarily need to draw it to be able to see what's going on. I just like the visual when I'm doing these. I think it's a little bit easier. But as a time saver, if you're on the AP test and they give you a table, you wouldn't necessarily need to draw this unless you really need it as a reference. And even if you need it as a reference, you could draw a rough sketch that really doesn't match what it looks like, just to have a sketch of your trapezoids so that you know what your lengths will be. So if we solve this, 1/2 times 4 is 2. I'll have a 40 plus 72 plus 52 plus 8. I'm going to use my calculator to help me with these, but it wouldn't surprise me if they gave you something like this that is not calculator active on the AP test, because these numbers aren't that difficult to put together. So we have a 2 times 172, and 2 times 172 is a 344. So this would be 344. What's the unit of measure? Remember, gallons per hour times hours would be gallons to find our unit of measure. So 344 gallons, I would venture to say that's probably the closest estimate we've had to the actual area under the curve. So to go further with finding the integrals and the area under the curve, when we find the exact answers to these, they're not going to involve geometry at all. They're going to be more algebraic than anything else. And that's where we're going to use the antiderivatives and going backwards. And just for the sake of you having another example in your notes, I'm going to do this one using the trapezoid rule. And instead of separating it into 3 subintervals, I'm going to go ahead and separate it into all 6 so that you can see another example of the trapezoid rule. The first thing I need to do is draw the lines for my trapezoids. So here are my trapezoids drawn. And remember, with the trapezoid rule, all of these widths are going to be the same, and the height for all 6 of these would be a 2. All of the trapezoids have a 1/2 times the height. So if I bring out that thing they all have in common, 1/2 times 2, so essentially we have a 1 on the outside, times 40, plus 2 times 38, plus 2 times 36, plus 2 times 30, plus 2 times 36, plus 2 times 18, plus 8. I can put all that in my calculator, and notice here, 1/2 times 2 is 1. So we have a 1 times all of this in here. And I'm going to use my calculator for that. And I'm getting an estimate of a 344. And again, for the unit of measure, gallons per hour times hours is gallons. So 344 gallons would be a very, very close estimate because we've used so many trapezoids, and those trapezoids are so close to my original curve.